Hello, this is Professor Roman. Let us continue our lectures on linear algebra. We have talked about the standard matrix representation of a linear transformation from Fn to Fm. And that is a representation by matrices. Every linear transformation is represented by its standard matrix. We now want to generalize that to the fully faithful representation of linear transformations between any finite dimensional vector spaces, say V and W, not just Fn and Fm. So the first step is to fix an ordered basis B for V and an ordered basis C for W. Once again, we can use the coordinate maps to construct a matrix representation for any linear transformation from V to W. And this picture tells the whole story. Here is the map tau from V to W. Here is the B coordinate map, and here's the C coordinate map. Both of these, well, this map, because B has size n, V has dimension n, this is Fn, W has dimension m, so this is Fm. So this line here, this dotted arrow, is a map from Fn to Fm, and it is found by following this square. We take phi sub b inverse, then apply tau, then apply phi sub c. So that looks like this. This map is linear because it is the composition of three linear maps. So it is a linear map from Fn to Fm, and therefore it is represented by a standard matrix Let me find it here. There we go. This is the map. This is the notation for the standard matrix. But this notation is a little unwieldy. So we're going to write it this way. Tau in square brackets sub b comma c. That is analogous to the change of basis matrix notation m sub bc. And we will call this the matrix representation of tau, or simply the matrix of tau, with respect to the ordered bases b and c. And as before, one needs to mention the bases because the matrix depends on the choice of bases. And so we now get this beautiful formula. Tau of v c coordinates. To obtain the c coordinates of the image of v under tau, which is essentially obtaining tau of v. If we know its coordinates with respect to a known basis, we know the vector, is equal to the product of the b coordinate matrix of v and the matrix representation of tau with respect to b and c. So in short, you can determine tau of V from V using the matrix representation of tau. You have to pass to coordinate systems first, to coordinates. Okay. This is a very important formula. It will occupy, we will use it many, many times in the sequel. And this should look familiar to you. This derivation is essentially a generalization of the derivation we used to get the change of basis matrix. If you replace this, remember the picture we had before, this is phi sub b and this is phi sub c. If you set tau equal to the identity operator on V, you can collapse this to just V, because composing with the identity does nothing. And we get this earlier picture, and this was the change of basis matrix. This is the matrix representation of tau. So this is really the same thing here. This is a special case of this. And the same argument we used to find the form of the change of basis matrix works here. All we have to do is take V to be one of the B basis vectors. And so we'll call it U sub I. And so tau U sub I C coordinate system is equal to matrix representation of tau times the B coordinate matrix of U sub I, which again is the standard basis vector E sub I. And this is a matrix times E sub I gives us the ith column of the matrix. So the ith column of the matrix representation of tau is just the C coordinate vector for the image of U sub I under tau. Again, the change, so we'll recall that the change of basis matrix is just, forgive my terrible handwriting, do the best I can. So these are the U's are the basis B vectors, and this was the change of basis matrix. This is a special case of this where tau is the identity. In this case, a way to remember this formula for the change of basis matrix is to think of the B matrix as the old matrix and the C matrix as the new matrix. So the columns here are the new coordinates of the old basis vectors. The idea of old and new doesn't work quite so well here because we are, let's go back to the picture here. Here we could say B was the old basis, C is the new basis, but here B is a basis for V and C is a basis for W. So the idea of this being the old basis and the new basis doesn't work out quite so nicely. You could say that this is the domain basis and this is the codomain basis. That would be okay, but I think it's just simpler just to think of the B basis and the C basis. So what this formula says is that to get that the columns of this matrix are simply the C coordinates of the images of the B basis vectors, if that helps. One way or the other, though, you should be able to produce this formula at a moment's notice. You don't want to have to agonize over it, because we're going to use it quite a lot. So you take tau of the B basis, and you take the C coordinates, and you get the columns of the matrix. Now we can define the matrix representation map. This is the analog of the standard matrix representation. But instead of the standard bases, we have the bases B and C. So we use the same notation. Well, actually, it's not quite the same. Before, I could have written mu sub Sn comma Sm, but it's not good to have three levels here. It's difficult to read, and so I wrote the standard matrix representation that way. Here it's not a problem. So mu sub Bc is a generalization of the standard matrix representation. So I guess you could have called this the BC matrix representation map, but that's also a little bit awkward. So in any case, mu sub Bc takes any linear transformation from V to W and gives you its matrix representation with respect to the bases B and C. And this is also an isomorphism, just as this was. This was a fully faithful representation of linear transformations from Fn to Fm by m by n matrices. This is a fully faithful representation of linear transformations from an n-dimensional vector space to an m-dimensional vector space by m by n matrices. Okay? So how to show that this is in fact an isomorphism? Well, there are various ways to do that, and I chose one here that is as compact as I could make it, just so you could see how one might do that. Mu sub Bc, this matrix representation map, is actually a composition of two maps. The standard the standard matrix representation map, mu sub Nm, that I've been discussing here, that takes linear maps from Fn to Fm, two matrices, and this map that I call lambda, that maps a linear transformation from V to W to a linear transformation from Fn to Fm. And that's exactly what this map does if we go around here. So lambda of a linear map from V to W is this linear map from Fn to Fm. Tau gets surrounded by these coordinate maps. This one is phi sub b inverse. It's the inverse of the coordinate map. This one is the direct coordinate map. We've already seen that the standard matrix representation is an isomorphism, and I'm going to leave it to you to show that the map lambda, which you might say in loose terms and words, is surrounded by two linear maps, two isomorphisms, excuse me, that this is an isomorphism. So, in summary, just to go over this. This is one of the most important theorems that we have encountered so far. V and W are vector spaces over F. Dimension of V is n, dimension of W is m. B is a basis for V. It's U1 through UN. C is ordered bases, that is, for W. Don't care what the vectors look like for C. Don't need to worry about that. The matrix representation map, mu sub BC, sends linear transformations from V to W to their matrix representations. It's not, when we talked about the standard matrix representation, we were able to say that a linear transformation from Fn to Fm is matrix multiplication, namely multiplication by the standard matrix of the map. Here we can't say that quite. What we can say is that the application of tau can be obtained by multiplying by this matrix representation. And by obtained, I mean we start with the B coordinates. We start with a coordinate matrix for V, which is just as good as V, multiply by this matrix and end up with a coordinate matrix for tau of V. So it's not quite multiplication by this. Tau is not quite multiplication by this. If we pass the coordinate systems, then it is multiplication by this matrix. And this is the formula for the matrix. Apply tau to the B vectors, and then take the C coordinates. There's really no other way this could work. You can't apply tau to the C basis vectors because they're not in the domain of tau. So you don't need to you can't really get confused about whether you put the B vectors here and the C basis there or vice versa. The other way just makes no sense. So this map is an isomorphism, which in symbols means that the matrix representation of A sigma plus B tau is A times the matrix representation of sigma plus B times the matrix representation of tau. This also tells us, because of this isomorphism, that the dimension of the vector space of linear maps from V to W is the same as the dimension of the m by n, the vector space of m by n matrices, and that has size m times n. So we have our fully faithful representation of linear transformations between finite dimensional vector spaces as matrices. Okay? And not quite as matrix multiplication unless you, once you pass the coordinate matrices, then it is matrix multiplication. Okay. Now, here's a very important point. When V equals W, when we're dealing with linear operators on V, it is, shall we say, customary to use the same basis, set C equal to B. See, now W is V, so we're dealing with linear maps from V to itself. The bases B and C are both bases for V, and it is customary to use the same basis. It's really the same basis for the domain of tau as it is for the codomain of tau. Both of those are V. And so the formula reduces to this, because rather than write tau sub b comma b, it seems rather unnecessary, we'll just write tau in square brackets sub b. And so we get this formula. We're going to be concentrating on linear operators at some point, and so this will be the most valuable formula for us. Matrix representations are, the matrix representation map is an isomorphism. We just proved that. It's fully faithful representation. But it also behaves very nicely with respect to matrix products. And here is how that goes. We have 3 vector spaces, all finite dimensional, with ordered bases B, C, and D. If we take a linear map from U to V and one from V to W, we can take their composition, tau sigma. Its matrix representation with respect to B and D is the product of the matrix representations of tau from with respect to C and D, and sigma with respect to B and C. So in very loose terms, the matrix representation of the product or composition, if you want, tau sigma, is equal to the product of the matrix representations of tau and sigma. The matrix representation of a product is equal to the product of the matrix representations. And this is another reinforcement, or you might just say motivation, for defining the product of matrices the way it is defined, so that this formula will hold. Also, if we have a linear map from U to V that is invertible, then its inverse, that means it's a bijection and it has an inverse, the matrix representation of tau inverse with respect to the bases C and B is the inverse of the matrix representation of tau with respect to B and C. This is similar to a formula for the change of basis matrix from B to C and C to B, how those two relate, if you remember the formula. Proof here goes like this for part 1. We want to show that these two sides are equal. So let's start on this side. So we have the matrix of tau with respect to C and D times the matrix of sigma with respect to B and C. We apply that to an arbitrary B-coordinate matrix. So B-coordinate matrix for an arbitrary vector little u in capital U. That's the domain of sigma. Leaving this alone, tau CD, this product is the C-coordinate matrix of the image sigma U. Now we can take this product. It is the D-coordinate matrix of tau of sigma of U. And now we can treat tau sigma as a single linear map, and so which, by the way, goes from U to W, so it involves B and D. So this is the matrix of tau sigma with respect to B and D applied to the B coordinate matrix of U. And since this holds for all U, it holds for all possible column matrices, these two matrices must be the same. And the proof of part 2 is very short, and instead of going over it, I'm going to leave it for you to think about as good practice. Some examples for the derivative operator mapping polynomials of degree at most 4 to itself, and the standard ordered basis, we take the operator and apply it to each basis vector, and then we want to take the coordinates of these images with respect to B. This is an operator, so we use the same basis on both sides. So we take the image of the basis vector in B, then we take the coordinate matrices of those images, again with respect to B, the same basis. And we put those in the columns. So if we look back here again, for example, D of 1 is 0, and so its coordinate matrix with respect to any basis is all zeros. D of x is 1. Its coordinate matrix with respect to this basis is 1, 0, 0, 0, 0. Those are the coefficients of the linear combination. So we get 1 and 4 zeros. For 2x, the coordinate matrix with respect to B is 0, 2, 0, 0, 0. So we get this column. For 3x squared, 0, 0, 3, 0, 0. And then finally this one. That's a very nice matrix. The derivative has, actually B is the standard basis. The derivative operator with respect to the standard basis looks quite nice. It's only got non-zero entries on the super diagonal, and they're 1, 2, 3, 4, 5, 6, 7, 8, however many you need. So if we wanted to, say, compute the image of the operator D on a polynomial like this, of course, this is a very simple example. I just said if we want the derivative of this, well, there's no fuss there. It's just 1 plus 4x. Okay, but let's go through this example because it works for much more complicated cases. So if we want D of P of x, we'll settle for its B coordinate matrix, because then we can use that to actually get D of P of x. And that's the D matrix, the matrix representation of D times the B coordinate matrix of the vector P of x. So that's this matrix here, and this is the coordinate matrix for this. 5, 1, 2, 0, 0. Take this matrix product, you get this, and there's your 1 and your 4. So this is the coordinate matrix of this polynomial, 1 plus 4x. So what we have done here is we have reduced application of an operator to multiplication by a matrix. That's the whole point of this. And in this case, it doesn't really make much sense to do it. But if D was some other much more complicated linear operator, and the vector space was a more complicated vector space, it would be nice to reduce the application of an operator to a vector to simply matrix multiplication. We discussed this earlier when we talked about the fact that some bases are better than other bases, and the fact that applying a linear operator is generally considered more difficult than taking a coordinate matrix. Here's another example. We did remark earlier that a matrix is its own standard matrix. A equals the standard matrix of A with respect to standard basis, in other words. Okay. But, and we also spent a little time discussing the fact that there are really kind of two interpretations of A here. On this side, it's the operator A, multiplication by A, because we are taking a matrix representation, and that's done for linear maps. And this is the actual matrix. We don't need to think of it here as an operator, it's just the representation of this operator. Okay. But there's no reason why a matrix operator, such as A, has to be represented by its standard matrix. We can use any basis we want to represent. If you're having a little trouble with this, you can still write mu sub A. If we want to represent the operator mu sub A, multiplication by A, this is a linear map from Fn to Fm if A is m by n. Oh, in this case, A is n by n, so this is a linear operator on Fn. We can represent that by using any ordered basis. Okay? So let's do an example. Here's a simple matrix. So that's a matrix operator, multiplication by this matrix, or put another way, A is an operator which takes the first standard basis vector E1 to 1, 3, it takes E2 to 2, 4. You extend by linearity. This is an ordered basis, so let's find the matrix representation of A, again, as an operator, with respect to the basis B. We apply A to each basis vector and take the B coordinate matrix. That gives us the columns of this matrix. So you just do the matrix multiplication here, you get these two vectors, B coordinates. See, if B was the standard matrix, standard basis, we'd be done. You could just delete these and it would be 3, 7, and 5, 11. But B here is not the standard basis. So we need to actually determine the coefficients in the linear combinations that give these two vectors. So here's the first one, and so the B coordinate matrix is negative 1, 4. Here's the second one, B coordinate matrix, negative 1, 6. Therefore, while the standard matrix representation for A is A itself, the B coordinate representation for A is negative 1, 4, negative 1, 6. So when you use this for multiplication, you multiply by this matrix, you write your vectors and your images of vectors using the standard coordinate system. Here you must use the B coordinate system or you will get nonsense. Okay. So it's very important to remember that matrix representations depend on the choice of ordered bases, or for operators, ordered basis. I strongly suggest that if you are a little vague on this, you spend the time it takes to get it straightened out, because this is not something we're going to be doing, but understanding this will help you understand this whole concept of matrix representation of linear maps. And that is something we will be doing for the rest of the series. I said earlier that when you are dealing with linear operators, it is customary to use the same ordered basis for both the domain and the codomain. I didn't say it's required, because it's not required. I said it's customary. And that's just not a matter of arbitrary custom. There is a reason for this. And the reason can be found in this formula. This is the formula that says that the matrix representation of a product, tau sigma, is the product of the matrix representations. But look at the bases here. Sigma maps, I think it was U to V, and B was a U basis, C was a basis for V, tau maps V to W, actually, well, that's okay. Tau maps V to W, and so this is a V basis, and this is a W basis, and here is the U basis and the W basis. This is the only way this makes sense. What if we set sigma equal to tau? What if sigma and tau are equal? Then this side is the matrix representation of tau squared. This side is the matrix representation of tau with respect to CD, and this is the matrix representation of tau with respect to BC. There's nothing you can do with this. You can compute this matrix product, but you can't simplify this. We would like to generalize this so that we can get matrix representations for any power of tau. You can see, I think, what's going to happen if we do not take some of these bases to be equal. When this side is tau to the power 10, we're going to have 10 factors over here with a bunch of different bases. It's going to be a mess. But if we use the same basis throughout, if tau is a linear operator, it won't work for linear transformation that's not an operator, but if tau is a linear operator, we take the same bases, we get this. The matrix representation of tau squared is just the square of the matrix representation of tau. This formula, when all these bases are the same, these two matrices are the same. Now we can generalize. The matrix representation of tau to the nth power is the nth power of the matrix representation of tau. So if you think of this as a way to compute the n-fold application of tau, you apply tau n times, this reduces the problem of applying an operator 10 times to raising a matrix to the 10th power. But even more generally, because of the linearity of the matrix representation map, this works for any polynomial. As long as tau is a linear operator, we can take p of tau, p is a polynomial, that's another linear operator on the same vector space V. And now we can generalize this using linearity to the matrix representation of any polynomial in tau is that same polynomial of the matrix representation of tau. And that's going to be also very important for us.